All right, welcome to day 9. On the front of your calendars, you can be writing today's date next to day 9. So we got packet page 59 and 60 for homework tonight, and you can also be working on problem set on Delta Math if you haven't done that yet. You can be taking out your warm-up sheet and your homework, and we're going to do the warm-up together. So on the warm-up, we've got a volume question. And I should say we're going to need our calculator for this warm-up as well. So we'll give you a moment to be taking your calculator out as well. So whenever we have a volume question, we want to go right to the reference sheet. We've got a sphere here. So we have that V is equal to 4/3 pi r cubed. And notice they give us the volume, and then we want to find the radius. So we'll put the 288 pi in for volume, and we're going to work to solve for r. So to get r by itself, we're going to divide both sides by 4/3 pi. The pi's divide out, because anything divided by itself is just 1. So then we just have to do the 288 divided by 4/3. Now when you do that, I would suggest do the control divide to get your fraction button. Put the 288 in top, and then it's clear that the 4/3 is going in the bottom. So when we divide by the 4/3, we should get 216 left equal to r cubed. Well, I'm going to go to an aside for a second. If we had, say, x squared equals 36, we would have undone our squared by doing a square root. So that would have given us x equals 6. You undo a cube by doing a cube root. In a square root, it's implied when there's nothing there that it's really a 2. Since that's the root we see most frequently, it's assumed that it's a 2 if nothing's written there. For a cubed root, we're going to do a root, and there'll be a little 3 in the crevice there. So on your calculators, the cubed root is in the far left column, 2 below the control button. You'll have to do control and then the caret, and it will give you the template for the cubed root. So essentially it's the button just to the left of the x squared. You'll have to do control and then that button. You'll put the 3 in the little crevice and then the 216 in. And essentially your answer to a cubed root is what number times itself 3 times gives you 216. Well, 6 times 6 times 6 gives you 216. So therefore our cubed root of 216 is just 6. And we'll put our units on of inches. So you can put your warm-up away and we'll move over to homework. Most of the homework was just either filling into our surface area or volume formula for the sphere. Surface area, you do not get that formula on the reference sheet, 4 pi r squared. Think of that visual of a cover of a baseball. It was really 4 circles making it up. And then the volume, like we saw in the warm-up, is on the reference sheet, 4/3 pi r cubed. So in this first one, we basically just had to take our radius, fill it into the surface area formula, round to the nearest hole, so we had 113 centimeters squared because it is an area. 2 was just marginally more difficult because you had to divide the diameter by 2 to get the radius. We had 121 centimeters squared. 3, we're working with volume now. So 5.5 is 5.5 for the diameter, divide it by 2 to get our radius. 4/3 pi r cubed is our volume formula. So the nearest tenth, we get 87.1 inches cubed. And then 4 is very similar, just filling into the formula, you got 904.8 centimeters cubed. And then the last one. So this is kind of like one of our shaded area ones, but in this case it's volumes. So our strategy is we're going to take the volume of the whole box, which that's what I've got on the left there, the 14.25 by the 4 by the 19 times the 4.75. That gives us that 1286 and change number for the volume of the box. And we're going to take away the volume of each of the spheres. And whatever is left over is the space that needs to be filled with the packaging material so that the ornaments do not break. So if the height of our box is 4.75 from the 4 3/4, divide that by 2, and that tells us our radius of each sphere is 2.375. Fill that into our volume of a sphere formula, we get 56 and change. Multiply that by 12 because we get 12 of them, so we get 673 and change for our volume of all 12 spheres. Take that away from the volume of the box. Notice I have not rounded any numbers yet when I'm doing that. You only round your final answer. Keep any other ones out all the way. And then we're going to round to the nearest hundred. So notice it's not hundredths, it's the nearest hundred. So your answer should be something like 400, 500, 600, 700, 800, and so on. So we got 612 and change. The 100 that is closest to would be 600 inches cubed. Okay, we're going to look at two things today. We're going to look at, actually three things. We're going to look at cross sections. We're going to look at three-dimensional shapes that are formed when you spin a two-dimensional shape around some line. And then we're going to look at unit conversions. So we're going to start out on page 53. And the first thing we're going to talk about is a cross section. So imagine you have a three-dimensional shape and you take a slice of it in 2 dimensions. So what I like to think about with this is if you've ever gone to the deli at the supermarket and you get them to slice some deli meat. Well, think of like the giant thing of ham. It starts out as a three-dimensional thing, and then when you get the slices of deli meat, if you get it sliced thin enough, it's just about 2 dimensions. Yes, it has just a slight bit of thickness, but pretty much it's just 2 dimensions. And that's what I like to visualize when thinking about cross sections. So we're going to jump ahead actually for a moment to page 54. And then we'll come back to page 53. So what we have on page 54 is a whole bunch of different common three-dimensional shapes and just visualizing some different cross sections. So notice in that cube there, when we draw in a horizontal cross section, we're getting a square there. And we would get a similar idea if we are doing it vertically. With the cone, if you slice it so it's going right through the point, notice that cross section is a triangle. So the cross section would be like that darker shaded part of it. But if you do a slice that is parallel to the base, now you're getting a circle. So imagine again that you're slicing it as if it's like deli meat or like slicing vegetables. Depending the way you slice it, you're going to get different shapes. Now with our cylinder, if you slice it so it's parallel to the bases, notice we're getting circles. But if you slice it vertically, you are getting rectangles. And then here's some with a pyramid. So if we slice it parallel to the base, we're getting squares. But now if you slice it vertically, you're getting triangles. And then with the sphere, if you slice it, we're getting all different rounded type shapes. So if we go back to page 53, in this first one here we have a square prism because we have 2 squares and then rectangular faces. So if we slice it the way that it's looking now, we would end up getting a square for each slice. So sometimes you see blocks of cheese that are like this. So if we sliced it that way, each of the blocks of cheese would be squares. Now in this next one, the way we were slicing it, this is a triangular prism. So if we slice it parallel to our base there, we would end up getting a whole bunch of triangles. And then we actually saw this one on the previous page, but if we slice the cylinder vertically like that, we're going to get a rectangle. So as we move down to the bottom of page 53, we've got 4 different three-dimensional shapes, and we want you to slice them all horizontally. So slice is going left to right. Basically, they're going to be parallel to those bases that we're seeing. So we want you down below in the blank box to sketch what two-dimensional shape would it look like when we do a horizontal slice. And then we're going to pause the video for 2 minutes to allow you to do that. So go ahead and see if you can sketch those 4 blanks right now. All right, in this first one, if we're slicing horizontally, we should just get a circle. In the second one, if we slice horizontally, we should get a pentagon type shape. In the next one, it should look kind of like an L. And then the last one is just kind of like a blob type shape, but looks something kind of like that. So we already looked at page 54, so we're going to jump ahead to page 55 now. The main way that this shows up on the Regents is as a multiple choice question. So this one's not actually a multiple choice, but we'll see some multiple choice when we get down to question 4. So for A and B here, we saw each of these examples over on the previous page, and you don't have to flip over. I'm just going to show you them here. So in our cones, notice if we slice it going through the point, that was a triangle, and if we slice it parallel to the base, that was a circle. So the first one there is our parallel to the base one, so we have a circle. And the second one here, we're slicing through the point, so that's a triangle. Now I want to actually start with D down below. So when we slice through the rounded part, but it's not parallel to the base, in everyday language, we would probably call that shape an oval. But in mathematical language, that is called an ellipse. Now, when you eventually get to pre-calc, you're going to learn that an ellipse has some specific features to it. There's 2 things called foci, and actually all the points on the ellipse are a consistent sum of the distances from those 2 foci. That's not anything we have to worry about for right now, but that's just the mathematical name of the shape that we in everyday language would call an oval. Now in C, if we have half of a circle, we would call that a semicircle. So here in this one, we have half an ellipse, so this would be considered a semi-ellipse. All right, down in 4, we're going to work with a cone again. This one's multiple choice. We want to know which one is not a possibility of a cross section in a cone. Now, spoiler alert, we just did the cone up above. So we're going to give you maybe 30 seconds. We'll keep the video running, but we'll give you 30 seconds. See if you can pick which choice would not be a cross section for a cone. So the circle we saw above in choice A, that was horizontal to the base. The semi-ellipse we saw in choice C, that's when you go partly through the rounded parts and partly through the base. The triangle was through the point of the cone. So the square is the one that we can't get when doing a cone. So next we're going to work with a square pyramid. So here's an example of a square pyramid. So we need to think about which of these shapes can we not get from doing a cross section. So again, we'll give you 30 seconds. Feel free to discuss in your groups if you are unsure, but see within your groups if you can come up with a consensus of which one is not a possible cross section for a pyramid. All right, the square we see over on the right there, so we can rule out choice B. The triangle would be if we sliced it vertically right through the point. Now, of the two remaining ones, there's no way to get a curved edge from the pyramid. So C is going to be the one that will not work. And just to show you how you could roughly get A, so here's a pyramid. And notice the cross section there we can see on the right is roughly a trapezoid. Basically, you would have to slice it kind of diagonally through two of the triangular faces that are opposite each other, and that would produce a trapezoid for you. All right, last multiple choice one. We want to know which figure, if you did horizontal cross sections, would they all be congruent? Congruent means they're exactly the same. So first off, we have the cone. So we dealt with a cone in this scenario here. Well, let's look in the top left. We saw a horizontal cross section is a circle. If we did lots of different horizontal cross sections, so maybe like another one would be here, notice those circles are not exactly identical. They're different sizes, so the cone would not work. Next up, we have a sphere. So here's my sphere. If I sliced, say, towards the top horizontally, that should create a circle. If I slice towards the middle, it'll also create a circle, but those circles will be different sizes because across the sphere is greatest at, if you go through the center, through its diameter. Next up, if we have a prism, so we had a picture of a prism on the first page. So let's look at B right here. Here's a good example of one. So here is a triangular prism. If we slice that horizontally, notice all of the slices going horizontally this way are all going to end up as that triangle shape. So therefore, that's our one that we're going to want. The pyramid, if we sliced it horizontally, which we saw in this picture, we'd have all different size squares, so those slices would not be congruent. Okay, so that concludes our portion of class looking at cross sections. The second portion of class is we're going to take two-dimensional shapes and spin them around a line in 3 dimensions. So what I want you to think about first is a ceiling fan. When a ceiling fan is turned off, usually, so you have some center part and there's some blades of the ceiling fan. So it may look something like that when it's turned off. But when the ceiling fan is turned on and you look up at it, you don't see the individual blades. It really just looks like a full circle. So that's kind of the idea we want to think about here. If we take this triangle in part A and we just repeatedly spin it around line M, imagine it's being spun really fast. We want to think about, well, what shape is it going to look like three-dimensionally as it spins around? Well, as it spins around, this bottom point here is going to make a circle. This point is on the line, so it'll stay the same. So this is just going to end up being a cone. In B, as this rectangle spins around this line really fast, this point here, just like in the cone, will make a circle. This point here will make a circle as it spins around. So this one's going to end up giving us a cylinder. This one here is intended to be a half circle. So as it spins around, it's going to create for us a sphere. Now, if you've got a circle that's away from the line, this is going to make, let's see if I can draw this very well. We'll have a gap as it spins around. So it's actually going to end up, because we'll have like something like that and something like that. It's going to make a donut shape. And my drawing does not really do it justice. But basically, as that circle spins around, imagine like a donut or a bagel. imagine like a donut or a bagel. Really, if you slice that donut or bagel going around, they would all just be individual circles that you're slicing. If we go down to the bottom, we'll see some more of these. So if this rectangle spins around, notice there's some gap. So it's going to end up looking something like this. So it's basically going to be a hollow cylinder. And what I like to think about is those snacks combos that are like the pretzels and then have some type of filling in the middle. Imagine if that filling was gone, it would kind of end up looking like this. When we had a half circle, we had a sphere. Well, if we've got that, but with a little bit missing, basically what this is going to create is a hollowed out sphere. Well, this shape, I like to think of it as a triangle and a rectangle. So it's kind of like A and B combined on top. So this part will give you a cone, and that part will give you a cylinder. So we'll say a cone on top of cylinder. And then this last one, again, there's some gap. So as it spins around those points, this is going to make a hollow cone. So think of like an ice cream cone or like a snow cone holder or something like that. Now, when this idea has shown up on the Regents, it is one of two things. Either they give you the original picture like we had here, and then they give you 4 choices for the shape, or they tell you the 3-dimensional shape you want, and they give you 4 different pictures that the 2-dimensional shape might be rotated around, and you got to pick which one would make that 3-dimensional shape. So that concludes our second part for today. So the third and final thing we're going to look at is over on page 58, and we're going to look at conversions. So with conversions, we're going to look at converting with the metric system. So for example, if we had meters, what if we wanted to convert it to kilometers? Or what if we had grams and wanted to convert it to milligrams? So so where it says copy this down, I added this right in your packet this year, so you don't have to copy it down. And in years past, I had students copy it down. Basically, from this chart, you just find where you are starting and then where you're going to. So let's say you are starting at meters and you wanted to go to millimeters. Well, to get to meters, you've got to go to decimeters, centimeters, and then to millimeters. Well, notice that's 1, 2, 3 jumps to the right. So if you want to go from meters to millimeters, all you have to do is move your decimal 3 to the right, and that moves the meters to millimeters. So we're going to use this as a tool to help us out. So we're going to move down to the bottom, and we're going to do some conversions. So our first one, we are starting with meters, and we want to go to kilometers. So we're going to go jumping 1, 2, 3 to the left. So a kilometer is a bigger unit of measure than a meter. So therefore, whatever your meters is, it should become a smaller number of kilometers. So first off, identify where the current decimal point is in your meters. Well, we have an integer of 400, so the current decimal point is after that second zero. Meters to kilometers, we did 3 jumps to the left. So we'll just take our decimal point, we'll go 1, 2, 3 to the left, and that's where our decimal point will now be. So we're going to have 0.4. And then when you have decimals, any zeros on the end, you don't have to write that because otherwise there'd be an infinite number of zeros. So we have 0.4 kilometers. So we're using this as a tool to help us with that. So now we're going to go centimeters to meters. So here's centimeters. here's meters. So we're going 1, 2 jumps to the left. So identify where your centimeters decimal point is. We're going to move 1, 2 to the left. So we're now going to have 4.8. And you don't have to write the 0 after that, but you could. It wouldn't be wrong if you did do it. So we'll do one more together, and then we'll pause for a minute to let you try the other few. So next one, we are going millimeters, and we want to end up with centimeters. So notice we're going 1 to the left. So our current decimal is after the 8. If we move 1 to the left, we now have 0.8 centimeters. So we're going to pause for 2 minutes to see if you can do those other 3. All right, we're going liters to milliliters. So here's liters. We want to go to milliliters. So we're going 1, 2, 3 to the right. So I'm going to bring it down here just so we have more room. So here's our decimal right now. We are going 1, 2, 3 to the right. Well, all those blanks we just fill in with zeros. So this is 5,000 milliliters. So 120 milligrams going to grams. So here's milligrams. We want to go to grams. So we're going 1, 2, 3 to the left. So here's our decimal point. If we go 1, 2, 3 to the left, we now have 0.12 grams. If you put a 0 after the 12, that's fine, but you don't have to when it's decimal values, and it's just going to be zeros afterwards. Now, you can always think about if it makes sense. A milligram is a smaller unit of measure than a gram. So when you go from milligrams to grams, your number of grams should be getting smaller. And then the last one, we're going to from kiloliters. And we're going to move over 2 to the right. So start, I'm going to bring it down here just so I have more room. Start with your decimal. We'll go 1, 2 to the right. We've got to fill in a 0 there, so we have 940 now. So you'll see a handful of those unit conversions on your homework. Now, most frequently on problems that we will see, it'll be pretty basic conversions, and it's usually going to be centimeters to meters is the most common one that we see. So knowing that there are 100 centimeters in 1 meter, so that's really a move of the decimal point twice in either direction, depending which way we're going. That's the main one that we're going to have to worry about. Any time left in the period, you are free to work on your homework and have a great rest of your day.